So welcome back to our third chapter of paper number 8, Modern and Nuclear Physics. Up till now we have completed the two chapters. These two chapters belong from the modern physics section, that is the photoelectric effect and the X-ray. Today we are going to see the third chapter of this paper and the first chapter of the nuclear physics section. The title of this paper is Nuclear Forces and Models. Let me share the screen first. Then we will see that what we are going to cover in this lecture. The title of the chapter is Nuclear Forces and the Models. In the today's actual, the total number of articles in this particular chapters are introduction, binding energy, nuclear stability, then two types of models, liquid drop model and shear drop models, and then we have to cover the different nuclear reactions, particularly nuclear fission and nuclear fusion. Now for today's lecture, I will cover these three articles, including the introduction on the nuclear physics. Now, as the title is the nuclear physics, first of all, I would like to throw the light on the introduction that what is nuclear physics. From the name itself, it is very clear that nuclear physics is the branch of physics which deals with the study of properties and nature of the nucleus. That means, element. Element, it is made up of large number of atoms. Atom of every element, it is consisting of two constituents or two regions. One, it is the nucleus which is present in the center, and second one are the electrons which are revolving around the orbit, around the nucleus in different circular orbits. Now in chemical reaction, the electrons which are present in the orbit and particularly in the outermost orbit take the part, and that are the chemical reactions. Now in some reactions, nucleus participate or nuclear take the part, and that reactions are called as the nuclear reactions. Now throughout this particular section, we will consider about the nucleus. As we are dealing with the properties and different aspects of the nucleus, this section or this branch is of the physics is called as nuclear physics. Now nucleus as we know, it is made up of two important constituents, that is proton and neutron, isn't it? Protons are positively charged particle, while neutrons are chargeless, and therefore the net charge on the nucleus, it is positive charge, and around this positively charged nucleus, electrons are revolving in a circular orbit around this nucleus, isn't it? And why the electrons are revolving around the nucleus? Because these electrons for the revolution around the nucleus required centripetal force, and the centripetal force for this one, it is provided by the positively charged nucleus and negatively charged electron. Now that part is not our source of consideration here today, but we are dealing here in this article about the different properties of the nucleus. So we have to consider what are the constituent of nucleus, how the nucleus is formed, how much energy is required to break the nucleus, what are the properties of that constituents, what is the how the nucleus looks like, how many forces are there present in the nucleus, what is the functioning of these forces. All these things we have to cover in this particular section, and this section in which we will go to cover this one, it is nothing but it is called as nuclear physics. The first article that we are going to deal here today is the nuclear binding energy. Now just now I have told you that nucleus, it is consisting of two parts, it is proton and neutron. This proton and neutron, these are called as the constituents. In Urdu you are calling as ajza. These two constituents, that is proton and neutrons, they are combined together to form a nucleus. Now so let us consider that this is the proton, this is the neutron. These are at a certain space from each other. Now by applying the certain energy, we have to bring these two proton or this proton and neutrons combines together, close together, so that they will form a nucleus. And in bringing this proton and neutrons close together, certain amount of energy is required, and that amount of energy required to bring into together and form a nucleus is nothing but that is called as the binding energy. Or in the alternate way, you can define that. Let us consider that a nucleus is there. It is made up of one proton and one neutron. These two proton and one neutrons were in a combined position and they have formed the nucleus. Now this nucleus we want to break up. In order to break the nucleus, certain amount of energy is required. And that amount of energy required to break the nucleus into or to split the nucleus into its constituents, it is nothing but it is called as the binding energy, and it is denoted by the term EB. The binding energy is the energy by which nucleons are bound together. You may also define that binding energy is nothing but it is the energy by which the nucleons are bound together. Now see here, regarding this particular picture, if you see my cursor here, this is the nucleus. This is made up of proton and these are the neutron. These are combined close together. A nucleus, they are in the form of nucleus. Now, when this combined nucleon, that means when it is in form of nucleus, when the certain amount of energy is applied, that means by applying the binding energy, this nucleus is breaks up or splits up into its constituent and its mass gets increases. That means when the nucleons, that is protons and neutrons, are close together, that means they are in the form of nucleus, mass is less. And when this nucleus splits up and they get split into this constituent, that is proton and neutron, then the mass is get increased. So contrary to this one, we can also say that when proton and neutrons, they are away from each other, they possess their individual mass. And when the mass of one proton, mass of one neutron combines together to form a nucleus, you found that the mass of the nucleus is not equal to the sum of mass of its constituent, but mass of the nucleus is somewhat less than the mass of their constituents, or addition or sum of their mass of constituents. And this decrease in mass, this defect in mass, this loss in mass at the time of combination of their constituents to form a nucleus is nothing but it is called as mass defect. And this mass defect is nothing but it is converted into form of energy, and that energy it is called as the binding energy. And according to the Einstein's equation, there is a relation between the mass and energy, that is E rest mass energy can be determined by the equation E is equals to mc square, as you know, where m is the mass and c is the velocity of light in air. And you know, this equation of the energy mass relation, which is given by the scientist Einstein, play a very important role in the field of relativity. Now, total mass of the nucleons, that is nucleons means individual proton and neutron, is always greater than mass of the nucleus by an amount which is called as the mass defect, and it is given by the formula EB upon c square, where EB binding energy and c square or c is nothing but it is the velocity of light in air. Mass defect is the mass of individual nucleons minus mass of the nucleus, you can say. Mass defect represents the mass that is converted into energy, and that energy is called as the binding energy. If you want to see the formula for the binding energy, a nuclear binding energy for the nucleus is containing the Z proton and N neutrons. And therefore binding energy is equal to ZMH, that means mass of Z protons plus NMN, mass of N neutrons, minus mass of the nucleus into C square is nothing but it gives the binding energy, where MAZ, it gives the mass of the nucleus or the mass of the neutral nucleus containing the nucleus. The quantity in the parenthesis is nothing but it is the mass defect. One more thing I would like to share with you, that one atomic mass unit is equal to 931.5 MeV, that is millionth electron volts. Note that the equation does not include ZMP, the mass of Z proton. The equation contains ZMH, the mass of Z proton, and Z electrons combined as a neutral hydrogen atom to balance the Z electron included in that particular AZM, the mass of the neutral atom. The table of the atomic nucleides contain atomic masses of the nucleon and atoms in the atomic mass unit. You can see that the nuclear masses are measured in terms of atomic mass unit with carbon. For example, carbon nucleus defined having the mass as 12 atomic mass unit. Now, you should remember one atomic mass unit is equal to 1.66054 into 10 raised to minus 27 kg, or just I have told you it is 931.5 millionth electron volts. One more conversation you should know, that 1 electron volt is equal to 1.602 into 10 raised to minus 19 joule. It is also common practice to quote that rest mass energy, that is E0 m0 c square, as it fit here in the mass. Binding energy of the deuteron. You know, heterogen is the simplest nucleus. The simplest nucleus is the heterogen. It has a single proton. That is, it is H12. That is having the two mass number is 2, atomic number is 1, and it is called as the deuterium. Its nucleus, that is nucleus of this deuterium, it consists of a proton and a neutron. That means its atomic number is 1, means it is contain one proton. Its atomic mass number is 2, means it contain one proton and one neutron, and it combines together, or it bonds together to form a particle, and that is called as the deuteron. The binding energy of the deuteron, if you want to calculate, that it is given by one proton, that is mass of one proton, it is 1.008725 unit, plus proton plus neutron 1.008665 atomic mass unit, minus mass of the deuteron atom, that is 2.01. If you combine this 1.0078 or plus 1.0086 and subtract the mass of the pure or neutral nucleus from it one, and multiply it by that conversion of 931.5 MeV, that will give the binding energy of the deuteron. Now, see here that how this conversation is taking place, that comparison of atomic and nuclear scale and the binding energy. Now, the binding energy per nucleus. We know that proton and neutrons combines together to form a nucleus. When I want to break this nucleus, when I want to split the nucleus, that means we want to separate the neutrons and protons. That means total amount of energy required to break this one proton or one neutron or one constituent nucleon from this one, it is nothing but it is called as binding energy per nucleon. Most stable nuclides from the lightest to most massive, having the binding energy in the range from 7 to 9th million electron volts. If you calculate the binding energy per nucleus for large many particles, and we plot a graph between the mass number versus the binding energy per nucleon, the nature of the graph is of this type. And from this one, we found that along the x-axis, we have taken the mass number, that is 5, 10, 15, 20, 20, 25, 50, and onwards. These are the different mass number, that is different element having the different mass number. And on the y-axis, I take the binding energy per nucleon in MeV, of course. And I plot a graph. The nature of the graph is of this type. If you observe the graph, if you want to interpret the graph, you found that when the mass number is less, binding energy increases very sharply, reaches to maximum near about at 8.8 MeV, and then it starts decreasing. But this decrease is quite slow, that this portion, if you see my cursor, it looks like a constant, isn't it? And from this one, we conclude that one more graph I would have shown here, that we have started from this one, the mass number of the hydrogen, helium, lithium, boron, magnesium, calcium, ferron, and Z1, near about as zinc or ferrous, it is nearly this 8.8 MeV when the mass number is just 50. But when the mass number is increases from 50 to 200 or 150, then we found that the binding energy per nucleon decreases quite slow. That looks that this portion is almost constant, and that means from this one we concluded that in case of the heavy nuclei, the binding energy per nucleon, that is binding energy divided by total number of nuclei, it is constant, and therefore binding energy is equals to constant into number of nuclei. That and number of nucleons, just I have told you, it is nothing but it is the mass number, and it is denoted by the symbol A, and therefore we can conclude from this equation that binding energy is directly proportional to the mass number A, isn't it? This is the practical dependence of the mass number, and with this one we will stop here today. Remaining thing we shall see in the next period, that practical dependence of the binding energy, and then we will compare that how it can be seen. So we shall stop here today. Thank you for joining me. Have a nice time.